There is a world so close to us that, on the scale of the galaxy, it is practically within reach. Close enough that its light arrives in just over 4 years. Close enough that if anything has ever happened there, we are not looking across the universe to find it, we are looking next door. It is easy to think of space as distant by default, to imagine that whatever answers exist out there are hidden far beyond our ability to observe them clearly, scattered across thousands or millions of light years, diluted by distance and time. But that assumption begins to break down when you consider a star called Proxima Centauri. This star is not a distant abstraction. It is the closest stellar neighbor to our solar system, a faint red point that exists just beyond the reach of unaided human vision, yet close enough in cosmic terms that its presence defines the boundary between here and everything else. Orbiting that star is a planet known as Proxima Centauri b, a rocky world slightly more massive than Earth, moving in an orbit so tight that 1 year there lasts just over 11 days. On paper, it sits in what astronomers call the habitable zone, the narrow region around a star where temperatures could allow liquid water to exist. For decades, that single criterion has guided the search for life beyond Earth. Find a rocky planet in the habitable zone, and you may have found a place where biology could begin. But proximity changes the weight of that idea. A habitable world 30 or 40 light years away is a data point. A habitable world at just over 4 light years is something else entirely. It is not just a candidate, it is a neighbor. And neighbors carry a different kind of implication because they collapse the distance between possibility and reality into something measurable. For years, Proxima Centauri b existed as a calculation rather than a place. Astronomers detected it through the subtle motion of its host star, the slight wobble caused by the planet's gravitational pull. From that wobble, they inferred its mass, its orbit, its distance. But they could not see it. They could not measure its atmosphere. They could not tell whether its surface was covered in oceans or stripped down to bare rock. Every statement about it came with conditions attached. It might have an atmosphere. It could support liquid water. It depends. That uncertainty persisted because of where the planet lives. Proxima Centauri is a red dwarf, a type of star that is smaller and dimmer than our Sun, but far more volatile. These stars do not shine with steady consistency. They flare. They release bursts of radiation that can be intense enough to strip away the atmospheres of nearby planets. And because Proxima Centauri b orbits so close to its star, those flares do not dissipate before reaching it. They arrive directly, repeatedly, over timescales of billions of years. This created a tension that defined nearly every discussion about the planet. On one side, there was the possibility that it could still be habitable, that it might possess a magnetic field strong enough to shield it, or an atmosphere dense enough to survive. On the other side, there was the argument that no planet that close to such an active star could retain the conditions necessary for life over long periods of time. That whatever it once had would have been stripped away, leaving behind a silent, exposed surface. Both views were supported by models. Both seemed plausible, and neither could be confirmed. The question was not simply what the planet is like. The question was whether a world so close to us, one that meets the basic criteria for habitability, could actually sustain those conditions long enough for anything meaningful to happen. Whether proximity to the right region of space is enough, or whether something deeper, something less obvious, determines the outcome. That question remained unresolved until a new kind of observation became possible. Not an inference, not a simulation, a direct attempt to read the planet itself through the light of its star. When astronomers finally pointed the James Webb Space Telescope toward this system, they were not expecting a clear answer. They were expecting limits, constraints, refinements of what was already uncertain. What they found instead did not confirm either of the existing views. It did something more disruptive. It suggested that both sides had been asking the wrong question. Because the most important thing about Proxima Centauri b may not be whether it can support life now or whether it ever could in the simplest sense. The more difficult question is whether it had enough time to become anything at all. And that is a different kind of problem. One that does not begin with distance or temperature or even chemistry, but with timing. With the idea that a planet can sit in the right place, with the right ingredients, and still fail to cross the threshold simply because the window does not stay open long enough. To understand why timing might matter more than location, you have to look more closely at the kind of star Proxima Centauri actually is. It is not a smaller version of our Sun. It belongs to a category known as red dwarfs, stars that dominate the population of the Milky Way by a wide margin. Most of the stars in our galaxy are not bright, stable, sun-like objects. They are dim, long-lived, and magnetically active systems that behave very differently from the one we orbit. At first glance, red dwarfs seem ideal for life. They burn their fuel slowly, which means they can remain stable for trillions of years, far longer than the current age of the universe. If time alone were the deciding factor, these stars would offer more than enough of it. Planets orbiting them could, in principle, have vast stretches of time for chemistry to evolve into biology and beyond. That idea shaped much of the early optimism around planets like Proxima Centauri b. But the advantage of longevity comes with a cost. Because red dwarfs are faint, their habitable zones sit extremely close to the star. A planet must orbit at a very short distance to receive enough energy to maintain liquid water. In the case of Proxima Centauri b, that distance is so small that it completes a full orbit in just over 11 days. This proximity introduces a set of conditions that do not exist in the same way in our own solar system. One of those conditions is tidal locking. Over time, gravitational interactions force the planet to rotate at the same rate that it orbits its star, leaving one hemisphere permanently facing the star while the other remains in constant darkness. This creates a world divided into two extremes: a day side that receives continuous radiation and a night side that never sees the star at all. The stability of a global climate under those conditions depends entirely on the ability of the atmosphere to redistribute heat between the two hemispheres. That leads directly to the second complication: stellar activity. Proxima Centauri is not a quiet star. It produces frequent flares, bursts of high-energy radiation that can be far more intense than typical solar activity. On Earth, our magnetic field and relatively distant orbit protect us from the worst effects of solar flares. At the distance where Proxima Centauri b resides, those protections would need to be significantly stronger to achieve the same result. Over long periods of time, this constant exposure to radiation can erode a planet's atmosphere. High-energy particles interact with atmospheric molecules, stripping them away and allowing them to escape into space. If this process continues unchecked, a once thick atmosphere can gradually thin until it no longer supports stable surface conditions. Water, if it exists, can be broken apart and lost. The surface becomes exposed and the environment shifts from potentially habitable to hostile. This is where the central conflict around Proxima Centauri b began to take shape. On one side, there were models suggesting that a sufficiently strong magnetic field or a large initial inventory of water and gases could allow the planet to retain its atmosphere despite the star's activity. These models pointed to the possibility that even under harsh conditions, a balance could be maintained. Heat could circulate, water could persist, and life, at least in simple forms, could find a way to emerge. On the other side were models that emphasized the cumulative effect of billions of years of stellar flaring. Even if the planet began with a dense atmosphere, the argument went, the relentless radiation environment would eventually overwhelm any protective mechanisms. The atmosphere would thin, the surface would dry, and whatever initial potential the planet had would be erased over time. In this view, the habitable zone was misleading, a geometric definition that did not account for the long-term stability required for life. Both perspectives relied on simulations, on assumptions about atmospheric chemistry, magnetic field strength, and geological activity that could not be directly verified. The difference between them was not a matter of data, but of interpretation. And because there was no way to observe the atmosphere of Proxima Centauri b directly, the debate remained unresolved. What made the situation more complex was the role of the planet's interior. A planet is not just a surface exposed to space. It is a system with internal processes that can influence its atmosphere over time. Volcanic activity can release gases, rebuilding or sustaining an atmosphere even as it is being lost. The balance between loss and replenishment becomes critical. If the interior remains active, the planet may be able to maintain a thin but persistent atmosphere. If it cools and becomes geologically inactive, the atmosphere may not recover once it begins to decline. This interplay between external stripping and internal replenishment introduced another layer of uncertainty. It meant that the fate of Proxima Centauri b could not be determined by its orbit alone. It depended on its history, its composition, and the rate at which its internal energy was being released over billions of years. By the time the James Webb Space Telescope was ready to observe the system, the picture that had emerged was not one of clarity, but of competing possibilities. The planet could be a marginally habitable world clinging to its atmosphere under extreme conditions. It could be a barren remnant that had already lost everything that once made it promising. Or it could be something in between, a transitional state that did not fit cleanly into either category. The limitation was not a lack of ideas, it was a lack of evidence. Without direct measurements of temperature distribution, atmospheric composition, and energy flow across the planet, every conclusion remained provisional. The models could be refined, but they could not be confirmed. What was needed was a way to move beyond inference, to extract information directly from the system itself. Not by seeing the planet as a separate object, which was still beyond reach, but by reading the subtle changes it imposed on the light of its star. That required an instrument capable of detecting signals buried deep within noise. Signals so faint that previous telescopes could not isolate them. When that capability finally arrived, it did not simply add another layer of detail to the existing models. It challenged the structure of the debate itself. Because the data that began to emerge did not align with the expectation that the planet would clearly fall into one category or the other. Instead, it suggested that the categories themselves might be incomplete. That the question of whether a planet can support life cannot be separated from how long it can maintain the conditions required for life to develop. And that shift from possibility to duration is where the next part of the story begins. The first hint that something is wrong with how we think about life in the universe does not come from a dramatic discovery, but from a quiet constraint hidden in plain sight. Time is not just a background variable, it is the main filter. For decades, the standard model of habitability treated the habitable zone as a spatial problem, a band of distance where liquid water could exist. But Proxima b forces a shift in perspective. It suggests that habitability is not just about where a planet is, but how long it can remain there under stable conditions. And that distinction changes everything. Because if the duration of stability is shorter than the time required for complexity to emerge, then habitability becomes a race that most worlds are destined to lose. On Earth, life appeared relatively early, but complexity did not. For billions of years, evolution moved slowly, constrained by chemistry, environment, and chance. The leap from microbial life to multicellular organisms was not guaranteed, and it was not fast. It required sustained energy flows, environmental consistency, and a sequence of contingent events that cannot be assumed to repeat easily elsewhere. This is where Proxima b becomes more than a nearby exoplanet. It becomes a case study in failed timing. The data suggests it may have had a window, perhaps 1 to 2 billion years, where conditions allowed liquid water, a moderate atmosphere, and active geology. In absolute terms, that seems generous. In biological terms, it may be insufficient. If Earth is the only example we have, then 1 to 2 billion years corresponds not to forests or animals or intelligence, but to bacteria, to chemistry that is alive but not yet aware. And if that is the general pattern, then most habitable worlds may never reach the stage where they produce anything capable of observing the universe back. This reframes the Fermi paradox in a subtle but powerful way. The silence we observe may not be because life is rare, but because advanced life is delayed, and the windows that allow it to emerge are often too short. Civilizations may not be destroying themselves. They may simply never have the time to begin. This idea, sometimes called the timing problem, does not require catastrophic events or hostile physics. It requires only that the processes governing planetary evolution and stellar behavior impose limits on stability. Red dwarf stars, which make up the majority of stars in the galaxy, introduce exactly these kinds of limits. Their habitable zones are close-in, exposing planets to tidal locking, stellar flares, and atmospheric erosion. The cold trap mechanism, observed or inferred on Proxima b, illustrates how these factors interact. On a tidally locked planet, the night side can become a permanent sink for atmospheric gases, freezing them out over geological time. Meanwhile, stellar radiation strips away what remains. The result is not a sudden collapse, but a gradual thinning, a slow transition from potentially habitable to definitively barren. This is not a rare outcome. It may be the default trajectory. And if that is true, then the concept of a continuously habitable zone, a region where conditions remain stable long enough for complex life to develop, becomes far narrower than previously assumed, perhaps vanishing entirely for certain classes of stars. The implication is uncomfortable. It suggests that the universe may produce many worlds that almost succeed, worlds that begin the process of life, perhaps even sustain it for long periods, but never cross the threshold into complexity. Worlds that are not dead but unfinished. Proxima b, in this interpretation, is not an outlier. It is an example, a glimpse of a common outcome that has simply never been observed directly before. And this is where the narrative becomes more difficult to resolve, because the data does not stop at atmospheric loss or thermal gradients. It includes something else, something that refuses to fit neatly into the model. A faint spectral feature, persistent across analyses, associated with a molecule that on Earth is strongly linked to biology, dimethyl sulfide. The signal is weak. It sits below the threshold required for confirmation. It can be explained by non-biological processes, though not easily. It is exactly the kind of ambiguity that science encounters at the edge of detection. And yet, its presence changes the context entirely. Because now, the question is no longer just whether Proxima b could have supported life, but whether it did, and whether we are seeing the residue of that process at the very end of its viability window. If the timing problem is real, then Proxima b may represent a world where life began but did not have time to become complex. A world where biology existed, perhaps for hundreds of millions of years, shaping its environment in subtle ways, leaving chemical traces that persist even as the conditions that supported it fade. This possibility introduces a new category into the search for life. Not just habitable worlds and not just inhabited worlds, but post-habitable worlds with residual biosignatures. Worlds that are no longer alive in any meaningful sense, but not entirely silent either. Detecting such worlds is fundamentally different from detecting active biospheres. The signals are weaker, more ambiguous, and more easily confused with abiotic chemistry. They require longer observations, better models, and a willingness to accept uncertainty. But they may also be more common. Because if the timing constraint is widespread, then there may be many more worlds that once hosted life than worlds that host it now. This shifts the strategy of astrobiology. Instead of searching only for strong, unambiguous signals of current life, we may need to interpret faint, decaying signals of past processes. We may need to become archaeologists of atmospheres, reading chemical layers the way geologists read rock strata, reconstructing histories from incomplete evidence. And that, in turn, raises a deeper question about what it means to detect life at all. If we find a signal that suggests biology existed but cannot determine whether it still does, have we answered the question we set out to ask? Or have we only complicated it? Because the distinction between a living world and a recently dead one may be impossible to resolve from a distance of 4 light years using photons alone. The atmosphere integrates time. It smooths over events. It carries signatures forward but without timestamps. A molecule detected today may reflect processes that ended thousands or millions of years ago, or processes that are still ongoing in hidden environments beyond our observational reach. Proxima b, in this sense, may never give us a definitive answer. It may remain suspended between interpretations, a permanent candidate rather than a confirmed case. And yet, even that uncertainty is informative, because it tells us something about the limits of observation, about the gap between what exists and what can be known. The universe does not present its history in clean, discrete packages. It offers gradients, overlaps, and partial signals. It requires interpretation, and interpretation always carries ambiguity. The shift from theoretical speculation to observational constraint that Proxima b represents is therefore not just a scientific milestone. It is a methodological one. It forces a re-evaluation of how we define evidence, how we assign confidence, and how we make decisions under uncertainty. It highlights the difference between possibility and probability, between detection and interpretation. And it does so in a context where the stakes are unusually high, because the question being asked is not just about a single planet, but about the prevalence of life in the universe as a whole. If a second independent origin of life is confirmed, even in the past tense, it would dramatically increase the likelihood that life is common. But if the evidence remains ambiguous, if Proxima b becomes an enduring question rather than an answer, then we are left in a different position. One where the universe appears capable of producing life, but not necessarily of sustaining it long enough for it to become visible or detectable or complex. A universe where biology may flicker into existence and then fade before it leaves a clear mark. And that brings us back to the timing problem, not as a hypothesis, but as a framework for interpreting everything that follows. Because if time is the limiting factor, then the distribution of life in the galaxy is not just a function of space, but of synchronization, of overlapping windows, of whether any two worlds are alive and detectable at the same moment. The silence we observe may not be emptiness, it may be misalignment. Worlds lighting up and going dark on timescales that rarely coincide. Civilizations emerging too early or too late relative to one another. Biospheres reaching their peak just before or just after the instruments capable of detecting them come online somewhere else. In that context, Proxima b is not just a nearby target. It is a test of whether we have arrived at the right time, not just technologically, but cosmically. Whether the moment we occupy intersects with the brief intervals when other worlds are readable, and whether what we are seeing now is a rare overlap or the faint edge of a much larger pattern that we are only beginning to recognize. If that pattern is real, then the next shift is not about detecting life, but about redefining what counts as evidence of it in a universe where most signals are incomplete. The classical expectation has always been clarity, a biosignature so strong that alternative explanations collapse under its weight. But Proxima b suggests a different regime, one where signals exist in tension with their uncertainties, where interpretation becomes as important as detection. The dimethyl sulfide feature sits precisely in that space. It is not strong enough to confirm, not weak enough to ignore, and its persistence across independent analyses forces a response that is neither acceptance nor dismissal. This is where science becomes slower, more deliberate, and more revealing. Because the problem is no longer whether we can measure something, but whether we can understand what that measurement implies in a system we cannot touch. Every step forward requires disentangling overlapping processes. Stellar activity masquerading as atmospheric chemistry, geochemical pathways imitating biological ones, noise shaping itself into patterns that resemble meaning. The follow-up campaign built around Proxima b reflects this difficulty. It is not a single observation, but an accumulation. Dozens of transits layered over years, each one adding a small increment of signal, each one reducing uncertainty without eliminating it entirely. The method itself is a recognition that certainty, if it comes, will emerge gradually rather than arrive all at once. And in that gradual process, another implication begins to take shape, one that extends beyond Proxima b itself. If the most accessible world we can study produces an ambiguous result, then ambiguity may be the rule rather than the exception. The expectation of a clean answer may be a bias carried over from laboratory science, applied to a domain where experiments cannot be repeated and variables cannot be controlled. In astronomy, and especially in astrobiology, we observe outcomes, not processes. We see the integrated result of billions of years of evolution compressed into a spectrum measured over a few hours. The challenge is not just detecting signals, but reconstructing histories from them. This turns every potentially habitable planet into a kind of statistical problem. Not a single yes or no, but a distribution of possibilities weighted by incomplete evidence. Proxima b becomes the first data point in that distribution, not because it is unique, but because it is close enough to study in detail. Its role is not to answer the question of life, but to calibrate how we ask it. And calibration changes expectations. It forces a reassessment of how many observations are needed, how strong a signal must be, how many independent lines of evidence must converge before a claim can be considered reliable. The lesson from past false positives, from ambiguous meteorites to debated atmospheric detections, is that the threshold must be high. But the lesson from Proxima b may be that the signals themselves rarely rise to meet that threshold in isolation. Instead, confidence may have to emerge from convergence, from multiple weak indicators aligning in a way that becomes difficult to explain without invoking biology. This is a fundamentally different mode of reasoning. It is closer to inference than detection, closer to building a case than finding a proof. And it introduces a new kind of uncertainty, one that does not disappear with more data, but becomes more precisely defined. As the signal-to-noise ratio improves, the question does not simply resolve, it sharpens. Alternative explanations are constrained, but not always eliminated. The space of possibilities narrows, but may never collapse to a single point. This is where the philosophical dimension begins to intersect with the scientific one. Because if the universe only offers partial answers, then the boundary between knowledge and interpretation becomes an active part of the inquiry. We are not just measuring the cosmos, we are negotiating with it, extracting meaning from signals that were not designed to be understood. And in that negotiation, the limitations of our instruments are only part of the constraint. The deeper limitation is temporal. We are observing systems at a single moment in their evolution, with no ability to rewind or accelerate the process. Proxima b today is not Proxima b a billion years ago, and the data we collect now carries only indirect traces of that past. The timing problem reappears here in a different form, not just as a constraint on life, but as a constraint on knowledge. We are trying to infer long processes from short observations, to reconstruct timelines from snapshots. And the accuracy of that reconstruction depends on models that are themselves evolving. This creates a feedback loop. Observations inform models, models guide interpretation, interpretation shapes future observations. Proxima b sits at the center of that loop, influencing decisions about which molecules to prioritize, which wavelengths to observe, which planets to target next. It is not just an object of study, but a driver of methodology. And that influence extends forward in time into the design of future instruments. The limitations encountered in its observation are already shaping the requirements for what comes next. Higher resolution, broader spectral coverage, direct imaging capabilities that can separate planetary light from stellar noise. Each of these advances is motivated by the same underlying need: to reduce ambiguity. But even as technology improves, the possibility remains that ambiguity is not just a technical problem, but a fundamental feature of the data. That there are limits to what can be known from a distance, no matter how precise the measurement becomes. If that is true, then the search for life becomes less about finding definitive answers and more about mapping probabilities, about building a statistical understanding of how often certain chemical patterns occur, how they correlate with planetary environments, how likely they are to arise from biological versus abiotic processes. Proxima b is the beginning of that map. A single point, but one with unusually high resolution. And what it shows so far is not a clear signal, but a structured uncertainty. A set of observations that constrain possibilities without collapsing them. This may feel unsatisfying from the perspective of a question as fundamental as whether life exists elsewhere. But it is also how science progresses when it moves beyond first discoveries into deeper understanding. The initial question gives way to more precise ones. Not, is there life? But under what conditions does life emerge? How long does it persist? How does it alter its environment? How detectable are those alterations over time? Each of these questions requires its own framework, its own data, its own interpretation. And Proxima b contributes to all of them simultaneously. Not by providing answers, but by forcing the questions to become more specific. In that sense, the ambiguity is not a failure, it is a refinement. It narrows the space of ignorance, even if it does not eliminate it. And it prepares the ground for the next stage of observation, where additional worlds are studied, additional data points added, patterns begin to emerge. Because one planet, no matter how well observed, cannot define a distribution. It can only suggest one. The real shift will come when Proxima b is no longer alone in its level of detail. When multiple nearby planets have comparable data sets. When similarities and differences can be compared directly. Only then can the timing problem be evaluated statistically rather than anecdotally. Only then can we begin to see whether Proxima b is typical or exceptional. But until that happens, it remains both a clue and a question. A world that has already reshaped the way we think about habitability, and that continues to resist a final interpretation. And somewhere within that resistance, within the persistence of a signal that refuses to resolve cleanly, is the possibility that what we are looking for does not present itself in the way we expected. And if that moment of overlap is as fragile as the data suggests, then what we are really confronting is not just a question about life, but a question about alignment across time. Because every process we have been describing operates on its own independent clock. Stars evolve on trillion-year scales. Planets cool, lose atmospheres, and transition between states over billions of years. Biology, at least in the only example we know, requires a comparable span of stability to move from chemistry to complexity. And technological civilizations, the only ones capable of detecting any of this, occupy a window so narrow it is almost negligible by comparison. The intersection of these timelines is not guaranteed. It may not even be likely. It may be rare in a way that is not obvious when each component is considered separately. A planet can be habitable without being inhabited. It can be inhabited without producing intelligence. It can produce intelligence without that intelligence developing the tools to observe the universe beyond its own atmosphere. And even if all of those conditions are met, the signals produced may not persist long enough or strongly enough to be detected from interstellar distances. What Proxima b introduces into this already complex picture is the possibility that even when life does begin, even when biology starts to modify a planet in detectable ways, the window during which those modifications remain visible may close before any external observer is capable of seeing them. Not because of catastrophe, but because of gradual planetary evolution. The atmosphere thins, the chemistry shifts, the signals fade, and somewhere else, on another world, Observers emerge just late enough to catch only the final traces. This reframes the silence of the universe again, not as absence, not even as rarity, but as a kind of temporal misalignment. A galaxy full of processes that rarely synchronize. Worlds passing through habitable phases at different times. Biospheres rising and falling out of phase with one another. Signals appearing and disappearing in ways that do not overlap. In that context, detection becomes less about distance and more about coincidence. Not just being close enough to measure, but existing at the right moment to do so. Proxima b may be the first time those conditions have been even partially satisfied. Close enough, recent enough, and still active enough to leave something behind that our instruments can detect. And yet, even here, even at the most favorable target we have, the result is not clarity but ambiguity. A signal that suggests but does not confirm. A history that can be inferred but not directly observed. This raises a final, more difficult possibility that the universe does not easily allow its biological history to be read from a distance. That the traces of life, especially simple life, may be subtle, transient, and easily erased. That what we are capable of detecting is not the full distribution of life, but only the narrow subset that produces strong, persistent, and unambiguous signals. If that is true, then our current search strategies may be systematically biased toward rare outcomes. We may be overlooking the more common scenario, where life exists briefly, leaves faint chemical signatures, and then disappears, without ever becoming detectable in the way we expect. Proxima b sits at the boundary of that realization, not clearly alive, not clearly dead, but in a state that forces us to confront the limits of both categories. And in doing so, it shifts the question one last time. Not just how many worlds host life, but how many worlds host life long enough and visibly enough to be seen by others. This is not a question that can be answered with a single observation, or even a single generation of instruments. It requires a population, a distribution, a map built from many points of data across many systems. But every map begins with a first point, and the first point does not define the pattern. It only reveals that a pattern might exist. Proxima b is that point, a single coordinate in a space we are only beginning to chart. And what it suggests, quietly, is that the universe may not be empty, but out of sync. That life may not be rare, but fleeting. That intelligence may not be unique, but temporarily isolated. And that the reason we do not see others is not because they are not there, but because their moment and ours do not coincide. If that is the case, then the fact that we are here now, with the ability to ask the question and the tools to begin answering it, is itself part of the phenomenon we are trying to understand. Our observation of Proxima b is not separate from its history. It is one endpoint of a chain of events that began with the formation of that system billions of years ago, and has now, through a sequence of contingent steps, produced a situation in which one world can look at another and attempt to reconstruct what happened there. Whether that reconstruction will ever be complete is uncertain. Whether the signal we are seeing will resolve into evidence of life or dissolve into a non-biological explanation remains open. But the deeper uncertainty is not about the outcome of the follow-up observations. It is about what kind of universe would produce this kind of situation at all. A universe where the nearest potentially habitable world is already past its peak. where the signals we detect are at the edge of disappearance, where the alignment between observer and observed is so narrow that it feels almost accidental. And if it is accidental, if this overlap between our technological moment and Proxima B's fading signals is just one of many possible non-overlapping timelines, then there may be countless other worlds whose stories have already ended without ever being seen, and countless more whose stories have not yet begun to produce detectable traces. Which would mean that what we are witnessing now is not the answer to the question, but a brief intersection of two independent histories, just long enough for a signal to cross the distance between them and be noticed before it fades into something we can no longer interpret.